Good evening and welcome to the Exploratorium and to After Dark and this evening's presentation of Everything Matters, Tales from the Periodic Table. I'm your host, Ron Hipschman, and tonight we are going to be talking about a really interesting element, gallium. So we hope that you find this interesting. I hope you all have your collectible card. Now, you can fill in your set, I think probably outside, I guess. I didn't see them, but I'm sure outside we have the other cards. If you happen to miss the first 30 Everything Matters Tales from the Periodic Table, you can fill in your set too. But you have to keep coming to it so you get all 118. We haven't actually produced any more than tonight, so I can't help you with any more after gallium. So try and go outside and fill in your whole set. We started at hydrogen and we're now up to gallium. So we hope that you'll come to more of these. How many people have been to After Dark before? Raise your hand if you've been to After Dark before. How many is your first After Dark? Wow. Well, if you enjoy After Dark tonight, you know we have this every Thursday evening, and one of the best deals on the planet is to, I'm going to be commercial here, is to become an After Dark member. For like 45 bucks, you can come to 52 After Darks. That's a pretty good deal, less than $1 a piece for a whole year. And you can come on Friday evenings. During the summer, we're open Friday evenings as well, so it's a really good deal. We hope that you'll take advantage of that. So tonight's program is about gallium. We're going to have two speakers, myself, and we have a guest speaker as well. It'll be a total maybe about 60 minutes. We'll have some questions and answers at the end. I'm going to talk about the chemistry, the history, the application of gallium a little bit. And for about 20 minutes, I'm going to be followed by Sribanti Chowdhury, who is a professor at UC Davis, and she's going to share with us how these technologies have impacted the world and how she's been involved in actually developing some of these technologies. So let's begin with gallium. Gallium, we all are familiar, since you're coming to the Tales from the Periodic Table. There's the periodic table. And tonight, gallium is, we're going to go all the way down here in the periodic table. Gallium, it's the 31st element in the table. Its atomic number is 31, and that just tells you how many protons are in the nucleus. It doesn't tell you anything about the neutrons, just how many protons are in the nucleus. If there's 31 protons, got to be 31 electrons, and all the chemistry happens out there in the electrons. So that's what's important, is that number right there. If it's 31 protons, it's gallium. If you were here last month, if it's 30 protons, it's zinc. So, and all those elements in the periodic table have unique numbers of protons. But gallium is our subject for tonight. And I want to go not too far back, but I want to go back to this guy right here, Dmitri Mendeleev, and he's the guy that came up with the whole concept of the periodic table. He took some of the properties of the elements, he arranged them into kind of an order that seemed logical to him. Here's the paper from his 1869 paper. Let's just magnify that so you can see it a little bit better. Look how nice everybody could handwrite back then. I'm always impressed by that. If we arrange that to make it actually readable for you, there we go. So that's kind of his arrangement of these periods of elements that had common, the rows had common properties. And you'll notice, if you look carefully here, you'll see that there's a few of them there that have kind of question marks before them. These were elements that were not known during the time of Mendeleev. And he kind of gave them some names. You can see them here, there, and there. This is again turning that chart 90 degrees. There and there. These were elements that were not known yet, but he thought that he might be able to predict what they would be. And he gave them some names. There they are in kind of the classic arrangement that we're familiar with. These are the elements that were known at the time of Mendeleev. And these unknown elements he called eka-boron, the same column as boron, eka-aluminum, eka-silicon, and eka-manganese. And these turned out to be elements that were eventually discovered. Scandium, gallium for tonight, germanium, which is coming up in October, and technetium, which is quite far away from us here, a year away at least. His prediction of these elements was quite good. Let's just take gallium as an example. Here is kind of a table, and in this column here is what Mendeleev predicted just by knowing where they were in the table, and here are the actual properties. So you can see he got pretty close to the actual properties here. The first person that actually measured the density measured it wrong, and he said, go back and measure that again. I think you're going to find something different. And he went back and remeasured it, and by God, it was exactly what Mendeleev predicted. So, and the first guy that actually discovered gallium was this fellow here, Paul-Émile Lecoq de Boisbaudran. Sorry, have a hard time with that one. Let's just call him Paul. He discovered in the spectrum of some zinc ore, a line, a color of light being given off by that zinc ore that was not zinc. If you looked at that spectrum right there, there's it's kind of hard to see on the projector here, but there's a brighter purple, well, violet line there from an element that was as yet unknown. And so this Paul discovered that element, and he named it after his, so it was discovered spectroscopically. He named it, since he was a French chemist, obviously, he named it after his country. Well, and this is the sample that he used to discover a sample of zinc sulfide, which is it's a zinc mineral called sphalerite. And he called it Gallia, after the name for France, Gaul. And which eventually became, well, actually, there's an interesting story there, because he has a word in his name, Lecoq, which means the rooster. The Latin for rooster, by the way, is Gallus. So there's some debate about whether he actually named the elements sort of for himself as well as for his country, but he denied that. We know about denials now, don't we? And that eventually, of course, became gallium. Probably his press agent had the next day had him walk that back. Gallium does occur in a moderate concentration in one mineral called gallite. And this is a really beautiful mineral here, but this is three minerals all in one. So the gallite is kind of the silvery stuff that you see in there. But and though it does occur in somewhat high concentrations, this is a very rare mineral, so it's not a good source to actually mine for gallium, because the mineral itself is very rare. Gallium is mined from these two minerals, sphalerite and bauxite. And you'll notice that you don't see gallium in either of the formulas down here. It's in there as an impurity, but it makes up about 16 parts per million in the Earth's crust, and that is actually enough. It gets a little bit more concentrated in these minerals, but it makes it enough to be commercially feasible to refine it further once you've gotten the aluminum and the zinc from these two minerals. The USGS, the U.S. Geological Survey, estimates that there's about 1 million tons of gallium contained in the known reserves of this bauxite mineral and zinc ores. So there's a lot of it out there. If you actually, it's fairly expensive stuff, as opposed to like iron, which is pennies for a pound. Gallium is about $200 a pound. So it's not super expensive. I mean, you can go on to Amazon, and you can actually buy gallium on Amazon, and for $20 you can buy that much gallium, 100 grams of gallium or something like that. As a matter of fact, if you want to feel how dense this is, I'll pass these around. Now gallium is, you'll see here is, I'll give it to you and you can pass down that one. Gallium it's not a super dense mineral. We'll talk about that in a moment. But it's, like I said, it's not a super abundant element, but it's also not super rare either. If we look here, it's about the 25th most abundant element in the universe. So, there's 118 elements, so 25th abundant is not too rare. It makes up about 1/1,000,000% of the universe. If you look at the sun, you'd expect it to be about the same as the universe, because the sun was made out of the stuff from the universe, but it's actually a little bit more, about 4 times as abundant in the sun, because the sun is actually made from material that was from older stars that blew up, and so the sun has concentrated that a little bit. So the sun is kind of like a 2nd or 3rd generation star. It's about the 20th most abundant element in meteorites, and the 23rd most abundant element in the crust of the Earth, where we get our gallium from, and the 23rd most abundant element in the oceans. And in humans, it is non-existent. There is no gallium in your body. There's a lot of elements in your body, but no gallium. Now, as I mentioned, it is created in stars, and gallium is created only in supernova explosions. So the fact that there's any gallium here means that we are made of the remnants of supernovas. You and I are made of remnants of supernovas. That's kind of cool. It's like Carl Sagan used to say that we're made of star stuff. Now, I mentioned that gallium has 31 protons in its nucleus, but it can have a variable number of neutrons in the nucleus. As long as there's 31 protons, we call it gallium. And we call those other things with different numbers of neutrons, we call them isotopes. It comes from the word iso, the same, topes, place. So it means the same place in the periodic table, but they have different weights. And gallium has a lot of isotopes. If you add up the number of protons plus the number of neutrons, that's this number right here. So there's 31 isotopes of gallium that we know of right now. And of all of those 31, most of them are radioactive. There's only 2 of them that are actually stable. 69, gallium-69 and gallium-71. So you'd have to do the subtraction, but 71 minus 31, oh, I can do that one. 40 neutrons and 40 and 38 neutrons. Those are stable, non-radioactive. All the rest are radioactive. And of that, gallium-69 makes up 60% of all the natural gallium on the Earth, and gallium-71 makes up about 40% of the gallium on the Earth. Now, I mentioned the rest of them are radioactive. They each last a different amount of time. They sit there and then they decay. Some of the isotopes sit around a little longer before they decay, and some of them sit around a little less. These are all of the isotopes that last longer than 1 minute. And the longest one you can see here is gallium-67, which lasts for only 3¼ days, which means that there's really none of it on the surface of the Earth because it's all decayed by now. But you can get gallium by the decay of other elements higher up in the periodic table. So it does exist, but it doesn't exist in very high quantities. Or you can make it in reactors. As a matter of fact, gallium-67 is used. You can be injected with this and it goes to places in your body and concentrates there, and then they can detect the radiation. Sort of like a bone scan, but they use manganese for that. They use technetium, an element that's coming up, for that most of the time. But gallium is used in bioassays. If you look at the metal itself, you can see it in the test tube, but here you can actually see gallium crystals. They're kind of a pretty metal. Although they were playing heavy metal when you came in, it's not that heavy of a metal. It's kind of midway. Density is about 6 grams per cubic centimeter. You know what water is? What's water? 1, right? And I'll put a few more up here too. You can see here that iron is a good amount denser than gallium. So iron is denser, lead is a lot denser. And well, actually, let's take a look at it on a chart. I love these charts. I get these from periodictable.com. By the way, periodictable.com, awesome website. Periodictable.com was done by the guy who did this book, Elements, Theodore Gray. Awesome book. Available in the store. But I love this book. This is a wonderful book. Photography, the best photography of elements I've ever seen. Density, there are elements that are very dense up here, and there are elements, of course, like most of the gases that are very, very light down here. And I have a bunch of things on the stage right here. Sorry, guys, I'm moving out of the light here. But there's things down here ranging from maple to plastic to, well, I have tungsten as my densest element down there, to lead, to copper, to iron, to titanium, to aluminum, to magnesium, and there's where gallium falls. So gallium's kind of in the mid-range there, a little lighter than most metals, but not too light. You can feel it wherever the gallium is. You can kind of feel its heft there. By all means, come on up and after the talk and sample these things. Be careful with the tungsten. The tungsten is extremely dense, and lifting that brick of tungsten, you may think that it's actually stuck to the stage. It's not. Use both hands. Don't drop it on your foot. It will leave a mark. Gallium is actually really soft stuff. This is a table of hardnesses that often is used for minerals, Mohs scale of hardness, where the super soft stuff is 1, like talc, and the super hard stuff, like diamond, is 10, and gallium is way at the top there. So gallium has it's very, very soft. You can actually cut it with a knife. That's how soft it is. One interesting feature of gallium is its melting point. If you look at the melting point of gallium, it's very, very low compared to most elements. It's way down there. So the only elements that actually melt at a lower temperature are cesium, I have to go over here and look at it, are cesium, bromine, which is actually a liquid at room temperature, mercury, a liquid at room temperature, and the rest are gases. So it's a really low melting temperature. Don't do this, but if you put gallium in your hand, gallium melts in your hand at less than body temperature. So if you put a lump of it in your hand, it melts, just like M&Ms don't. However, the interesting thing about gallium is even though it melts at a very low temperature, it boils at a moderately high temperature. It's way up there you can see here up in the 2,000 degree-ish range. So there's a huge range from the melting point to the boiling point. That's not true of most metals. The boiling point and the melting point are fairly close together. Now I wanted to demonstrate the melting point of gallium here. I actually have a spoon here that I cast out of gallium. This is science. This is jokes that scientists play on each other. Okay, but I'm not going to play the joke on you. And I have some hot water down here. And I want to put some hot water in here. So let's get some nice hot water. There we go. So I'm going to take the spoon, and let's watch what happens to the spoon as I dip it in. Can you see it? Yep. Here we go. So if you served you this spoon with somebody with some really nice hot tea, you end up with a little puddle of gallium at the bottom. So when I finish tonight, we will put that in. We'll actually put it into some ice water, and it'll freeze up into a nice little ingot, and we'll do it again. We'll make a new spoon for it. Okay, back to the slides. Another interesting quality about gallium. If we go to this slide here, you may notice that this is a graph of thermal expansion. What portion of, say I make a rod that's 1 meter long, and I heat it by 1 degree Celsius, how much longer will it get? You'll notice that gallium is way up there. Aside from mercury, which has a super high expansion rate with temperature, gallium is the next one down for that. It expands quite a bit. By the way, the fact that mercury is the very top element here makes it really useful in thermometers. You put a mercury thermometer in your mouth, the mercury in the bulb expands and squeezes it up the capillary tube, and that's what makes mercury thermometers very sensitive. Gallium, although it melts at body temperature, that means it's not a real good element for thermometers. It is possible. I'll talk about a gallium thermometer in a moment. But because of this, it expands so much. It also has another unusual feature, and that is when you freeze it, normally when you make things colder, they get smaller by that ratio. Water, you notice the water, when water freezes, do you know what happens to water when it freezes? It doesn't continue to get smaller, it expands. Extremely unusual. There's not many substances that do that. Gallium is one of those substances. When it freezes, it gets bigger, which means that when you buy it, and you'll notice that those little tubes I passed around are made out of plastic. And that's because when you pour it in as a liquid and it freezes as a plastic, it gets bigger. So if you put it in a glass vial, it will shatter the glass vial. So all the bottles that we put them in are plastic bottles. Now, about that thermometer thing, you can make alloys with gallium. And this is you can make an alloy that actually freezes at about minus 20 degrees C, or about minus 2 degrees F. And you do that by combining gallium and indium and tin. Gallium, indium, and tin in chemistry is usually called stannous, or is S-T-A-N. So a Gallium metal actually is 68% gallium, 21% indium, and about 10% tin. And it stays liquid down below the freezing point of water. You can make this into a thermometer. And you can go out and you can actually buy this thermometer. And it's a mercury-free oral thermometer. It doesn't have any mercury. Of course, it does have indium and gallium and tin in it. But they're actually fairly non-toxic. And so you can actually, if you insist on having a thermometer that has metal that flows up a capillary tube as opposed to using an alcohol thermometer or a digital thermometer, probably much easier, the digital thermometer, then you actually can still get one, and it's called a Gallium thermometer. Pretty cool. Okay. I didn't really want to go into the applications yet, but let's go back a little bit to the things. The gallium atom is fairly large compared to hydrogen. We always kind of do this comparison. And again, its spectrum has that unique violet line, which is kind of hard to see in this slide, but it's there. And that's how they identified it originally. You can see that violet line in the solar spectrum. Now, if I take, here's the solar spectrum, and there's actually a dark line here. It's kind of hard to see again because it's so violet down here. But that's caused by gallium in the outer atmosphere of the sun. And this is the solar spectrum here. All these dark lines are caused by elements in the sun. So this really broad one here is due to hydrogen, and these are due to magnesium, and this is due to sodium, those two. So these, you can tell, isn't it cool that you can tell what the sun is made of without actually going there and scooping up a cup? That's pretty cool. Spectroscopy, extremely useful tool. Let's do a little some applications now. Gallium, when you combine it with a couple of elements like arsenic, for instance, is useful in super high-speed transistors, little switches. And these switches are really high speed. They can run at billions, they can turn on and off billions of times per second. You have these in your cell phone. These are MESFET stands for metal semiconductor field effect transistor. And these are used in all kinds of microwave circuitry. So that's one cool application. But I think one of my favorites, of course, is LEDs, which is why I decorated the table tonight. Actually, I'm going to turn these blue LEDs off because there may be a little, I should have turned them off a lot earlier. Everyone in the front row can go, finally. LEDs come in all colors, and I have, like, here, I did have some beautiful colored LEDs here. Can I move this forward? I can move this forward. Maybe turn it this way. Look at across the spectrum, red, orange, yellow, green, blue. There's a violet, there's actually a blue and there's an ultraviolet one there, a blinking LED. And this one, which has actually the bottom one there has 3 chips in it, a red, a green, and a blue. And you can vary them so you can make any color you want. Here's another sample set of LEDs, bigger sample. So you can make lots of different colors of LEDs, and they all have, but you'll notice one thing that's common among most of these LEDs. What's common? Gallium. Gallium is present in almost all of them. Not all of them, but most of them. 90% of them. If you look at, LEDs are actually a fairly new invention. 1962 was like the first kind of reddish LED, and that was aluminum gallium arsenide. So aluminum, gallium, and arsenic in there. Excuse me for a moment. Much better. So in 1962, we first had red LEDs, and we all remember back, well, some of us may remember back, the very first like calculator displays had red LEDs in them. The green LEDs in 1975 are created in a couple different ways. Gallium phosphide, gallium and phosphorus, which makes kind of a dim-ish green LED. But if you want it any brighter, they actually use a red LED and they double the frequency with a little crystal inside there. So a couple different ways you can make green LEDs. And in 1972, yellow LEDs, gallium indium phosphide or gallium phosphide again. But the big invention, the one that really allowed us to have lots of applications, and the holy grail was the blue LED. And the blue LED had to wait till 1994. Indium gallium nitride or gallium nitride, blue LEDs, invented by this fellow here, who also worked with two other fellows too, but I'm only going to show him for right now. He has a blue laser, also basically diode lasers are basically semiconductor LEDs that can produce a beam. And him and his two fellow workers did get the Nobel Prize for the blue LED. So significant was that invention because with the blue LED, you could make the white LED. And that was kind of the holy grail. How can we make efficient lighting? And the white LED here is actually a blue LED. Here's the blue LED, the gallium nitride blue LED. This is the blue light coming from the gallium nitride. And then they put something that glows when it's hit by blue light. It fluoresces. It's a phosphor, and it glows yellow. And so you add yellow to blue, and you get white. So this is the spectrum of white LED. It doesn't look like the spectrum of a regular light bulb. Let me move these over, because we're going to use those in a moment. Actually, these are blue. These are white LEDs right here. You see the yellow phosphors, and those phosphors glow when they're hit by the blue light. They glow yellow, and you add together the blue and the yellow, and you get the white, apparently white light, which gave us, finally, decent LED light bulbs, much more efficient LED light bulbs. They're very efficient, actually. If we compare them, here I can show you. Let's turn that on. Oh, that's kind of bright. So this is an incandescent lamp. This one here is the compact fluorescent lamp, and here is an LED lamp. These are each 40-watt lamps. Now, when I say 40 watt, that's really only applies to the incandescent bulb. That's how much power that incandescent bulb is using. Let's look at that. Well, they all produce about the same amount of light, as you can see. Well, this one doesn't until it warms up, a real disadvantage of compact fluorescent bulbs, in my opinion. I'm not a big fan of compact fluorescent bulbs, as you will see. It takes a while for them to warm up. LEDs do not take any time to warm up, neither do incandescents, although the incandescents put up a lot of heat. They're not very efficient. Look at how much power is used. I'm going to turn that off. It's too hard to look at. An incandescent light bulb uses, well, a 40-watt incandescent light bulb, not surprisingly, uses 40 watts of power. But look at a compact fluorescent light only uses 8.6 watts, and an LED only 7.3 watts. A little bit more efficient. These are fairly equivalent efficiency-wise. If we do a division, how much light do you get per watt? Incandescent bulbs, well, they kind of suck. They produce about 5% of the energy that goes into them goes into light, and the other 95%, if you put your hand over this, you'd realize it goes into heat, which is okay if you need to heat your house. But generally speaking, that's not why you put light bulbs in your house, not to heat it. So you can see that look at how much more you get, 64 lumens per watt, or a little over 60 lumens per watt compared to 12. That's hugely efficient. And then the lifetime, incandescents, I think I get more use out of my incandescents than this. I don't know where this figure came from. Compact fluorescent was advertised to us as lasting almost 10 times as long as your incandescent. But that, of course, anybody out here believe that? No, it's a lie. I have incandescent bulbs at home that are still running from the time I got my house 30 years ago, and I've replaced every compact fluorescent bulb that I've ever installed. But the LED bulbs claim to last a lot longer, and we'll see, because we haven't had them around long enough yet. But they have been lifetime tested, but this is a lie. And they have mercury in them. They have toxic metals in them. So, bad. It was a stopgap measure while we were waiting for LEDs to become more efficient, I guess. Well, okay, that's its only blessing. If you can make diodes of every color, since, well, like this laser that I'm using here, and I have others, you can make lasers. This is a barely visible violet laser. It's so violet you can barely see it. It's actually a lot brighter than you see here. Maybe you have a card here. Yeah, well, it looks a little brighter on that card. Or I have a green laser here, but here's a little brighter green laser. This is amazingly bright. Or, you can get lasers in red and all different kinds of colors. And these are just diodes. They're really LEDs, but they're special LEDs that have been prepared to reflect light back and forth and create laser light by stimulated emission. They amplify that light. Different talk. August next month. Lasers, full spectrum science. We'll do some laser work here too. Come back for full spectrum science next month. Lasers. And here you can see if you can get LEDs of all different colors, you can get lasers of all different colors as well. As a matter of fact, laser light shows now, they usually have a red laser, a green laser, and a blue laser, and then they combine those and you can make any color you want. Now, this is an interesting physics experiment. The sun makes energy by combining hydrogen and creating helium in the center of the sun. But in doing that, neutrinos, ghostly particles that hardly interact with anything at all, stream out from the sun. They don't interact with the sun. You have trillions of neutrinos passing through you now, every second. But they don't interact with you, fortunately. And so, so that means detecting them is really difficult to do. And one way to detect them was to take a very large vat of something and then allow the neutrinos to interact with that. And this is an experiment in Russia called SAGE, the Soviet-American Gallium Experiment. And this has the largest amount of gallium ever gathered in one place. It was 50 to 57 tons, it varied, of gallium in this experiment right here, down in these vats down here. And when neutrinos go through there, every once in a while, one would react with a gallium atom and change it into a germanium atom. And then you could separate, this is a very difficult experiment to do. You can separate the germanium out from the gallium and count how many neutrinos interacted. And that gives you an idea of how many neutrinos are coming from the sun. And this experiment discovered something really interesting. They only got 40% of the neutrinos that they were expecting to get from the sun. What was the explanation for this? And it has something to do with neutrinos being able to change their flavors in flight. They oscillate. But very interesting experiment. Also had some nice some politics that went along with it, because 50 tons of gallium is worth a lot of money at $200 a pound. And so the gallium was owned by the Russian government, and they needed to pay some mine workers, and they decided that they were going to repossess the gallium from the experiment. And the scientists didn't want them to do this, and they kind of objected highly vociferously, and Russian government sent in some form of military command to take the gallium away from the scientists. But one scientist figured out that if he unplugged all the locks and things like that, they couldn't get in, and that gave them some time to renegotiate, and they were actually able to renegotiate the gallium experiment and keep it running for another few years. So, kind of cool. That scientists fight back, yeah. One interesting thing that gallium can do, and you have to be very careful when you're holding on to gallium, and that is it can actually penetrate into the crystal structure of other metals, like aluminum. this is an aluminum lock, and it's normally very strong. You could not bust open this lock with a hammer. No matter how hard you tried, you could not bust this lock open with a hammer. But if you just take a little drop of gallium and put it onto the lock like this, the gallium actually goes into the crystal structure between the crystal grains of the aluminum, and 4 hours later, he can just take his hand and break the lock apart like that. Totally compromising it. So don't put gallium on anything that's aluminum, like laptops or things like that, because it will destroy the material. Very, very destructive. But it's really cool, the fact that actually gallium can work its way into that far into that crystalline structure of the aluminum in just 4 hours. I think that's stunning, actually. This is something that is a little familiar to us here at the Exploratorium. Our founding director, Frank Oppenheimer, worked on the Manhattan Project with his brother J. Robert Oppenheimer. And this, what you're looking at there, is actually not the real thing, but it's a simulated pit. It's the center of a plutonium bomb. That is a solid core of plutonium. You can see it's about 6 inches across. And the idea inside of an atomic bomb is you kind of compress this thing, and when you compress it, it will go critical and explode. But the plutonium cores, the plutonium is not a very stable metal, and to stabilize plutonium, they mix it with gallium. Yes, so gallium actually played a part in the very first atomic bombs. That pit, which was the very center of the bomb, was actually Frank's friend, Phil Morrison, who is a kind of really famous physicist who last taught at MIT. He passed away fairly recently. Actually carried that out to the bomb in the car. It's really great when you get physicists who come here and tell you these kinds of stories, that he actually carried a plutonium pit in the 57 Chevy. No, it was a 45 Chevy or something like that. No, it must have been earlier than that. Here, that pit goes in the middle of this. This is the device. This was the very first plutonium bomb that was set off at the Trinity site in New Mexico. This guy here is Dr. Bradbury. He later became the director of the Los Alamos labs, and there's a museum in Los Alamos, the city of Los Alamos, that you can see all this kind of really interesting history in. The nice thing about gallium, when we start talking about the biology of gallium, is that there is no biology of gallium. So it's not it has no biological function, so we can skip it. So I go to a fun thing here. A fun thing that gallium was used for was to make the world's smallest book. This is the world's smallest book here. And you can see here, this is the scale here. This line here is 50 microns long. That's 50 millionths of a meter. Hair is about 20 to 30 microns. So this would almost fit across the diameter of a hair. It's a little bit bigger than a hair. You can magnify it, and you can see it a little closer. These lines were etched in silicon. This is silicon. So they took some silicon like this, and they cut it into a wafer. Well, here's a wafer of silicon, except this silicon wafer is actually a solar cell, very thin. And then they sent a beam of gallium atoms at this wafer, and that's what caused the etching here. And this is really hard to read, but this is, the book is, let's see if I can read it here. It's called Teeny Ted from Turnip Town. So that's the book. And you could actually, this book cost $15,000 to make, by the way. It's the smallest book ever made, Guinness Book of World Records. It's carved on 30 little pieces of silicon. These lines here are just 7 billionths of a meter across. It's really small. So kind of a cool fact. So I'm going to go to a little haiku. We're coming up to the end. Melting in my hand, agent in nuclear bombs, feigning innocence. Next, Everything Matters, Tales from the Periodic Table, is germanium, but we're taking a break, so that doesn't happen until October. So on October the 18th at 8 will be our next element. I also mentioned the fact that we're doing lasers, but this month, full spectrum science is about heat and temperature. So, thank you.